So today we're going to start our first of 3 lectures on what's called the transient analysis of circuits. So I'm going to call this particular lecture the natural response of first order circuits. So there's a lot of words in here that you guys may not be familiar with, and that's okay. So the first thing that I want to talk about is what a first order circuit is. Okay. So a first order circuit is simply a circuit that is just described by a first order differential equation. So I'm sure a large portion of you guys are currently panicking because it sounds like we're going to be dealing with differential equations in this class, and we are, but they're going to be fairly simplistic, and we'll talk our way through how to solve those simple differential equations. We're only ever going to have to solve them today. As soon as we learn to solve them once, we're just going to come up with a method that uses that solution for literally everything. So realistically, not a whole hell of a lot of calculus going on after, let's say, 9 o'clock-ish today. All right. So a circuit that can be described by a first order differential equation is usually what we would call an RL or an RC circuit, meaning that we can lump all of the circuit elements together into some type of source and then a single equivalent resistance and then a single equivalent energy storage element. Whether it is a capacitor or an inductor will just be dependent on, what we've got to work with, okay? The natural response simply means that we are dealing with a source-free system. So that means we have a system where our excitation or our forcing function, be that a voltage source or a current source, is effectively removed from the circuit. And then we are seeing how the remainder of that circuit responds to that removal, which gets us into transient analysis, where transient simply means that our circuit is undergoing some change. So we're going to put all of those words together and talk about how we can analyze circuits that are undergoing some type of change or perturbation, okay? So I want to start with an RL circuit, okay? And so let's say that I have a system that looks something akin to this. So here I have some current source IS. It is a DC current. And I'm going to have a switch, okay? And so what I'm attempting to draw here is that our switch is closed at position A currently, and it will later on close at position B. And this transition will occur at some time t is equal to 0 when we start paying attention, essentially. Okay, bless you. Let me continue drawing the remainder of the circuit over here. Over on this side, I'm going to have some resistance, and I'm going to call this resistance REQ. So it represents the equivalent resistance of our system. And then over here further, I'm going to have some inductance LEQ. Okay. So I'm going to define a few things here, okay? So the first thing that I'm going to define is my inductor current, okay? So my inductor current, IL of T, will be the current that's flowing down through that resistor LEQ. And then I'm going to assign a voltage drop across that inductor. So this will be VL of T, like so. And I'm also going to assign a voltage drop across our resistance REQ. And I'm going to choose to put the positive polarity of that resistance on bottom. So this will be VR of t. Now, let me explain very briefly why I chose to put the positive polarity terminal on bottom here for how we are deriving things and first introducing this, okay? So if we look at this circuit for time less than t is equal to 0, okay, we're going to assume that our switch has been closed at position A for a very, very long time, okay? So what we essentially have is a current source IS in parallel with some resistance REQ in parallel with some inductance LEQ, right? If our switch has been closed for a very, very long time, we can treat this as if it is a DC circuit because any transients that we might have experienced have since died out, okay? So if we're treating this for t is less than 0 as a DC circuit, then what does our inductor look like? A short circuit, okay? So how much current is flowing through that inductor? All of it, so all of I of S. So essentially, we have some amount of energy that is being stored by that inductor LEQ, okay? Because there's a current flowing through it, there's energy stored. We know that the energy stored in an inductor is 1/2 Li squared, right? So after we switch over to being closed at position B, effectively disconnecting that current source from the resistor and the inductor current is going to continue to flow because we know that the current that's flowing through an inductor cannot change abruptly. And that inductor current is going to flow up through that resistor REQ, which is why I chose to put the positive polarity terminal on bottom, so that if I needed to use Ohm's law or anything like that, I wouldn't introduce extra negative signs. Okay. All right, so we have already established effectively that IL at t is equal to 0 minus, so this is approaching 0 from the left-hand side, is equal to IS. We know that IL at 0 plus must be the same as IL at 0 minus, because the current flowing through an inductor cannot change abruptly. So this value has to also be equal to IS. And the last thing that we need to sort out here is what IL trends toward when we allow a lot of time to elapse, which I'm going to call t is equal to infinity, okay? So we know that our inductor has some amount of energy stored in it at t is equal to 0. What's going to happen as time progresses for t greater than 0 is that resistor is going to gradually convert the energy that was stored in that inductor into heat, because that inductor is going to force current to flow around the system, and some current is going to flow through that resistor. And all a resistor can ever do is convert electrical energy into heat energy. We discussed this on our third lecture when we were talking about Ohm's law. So after a really, really long amount of time, I'm calling it t is equal to infinity, what we should see is that all of the energy that was initially stored by the inductor has since been converted into heat by the resistor. And so over time, our inductor current is going to settle down to a value of 0 amps because there's no source connected to the inductor anymore, right? When we switch that switch over from being closed at A to being closed at B, that current source is no longer connected to the inductor, so it shouldn't have any influence on what the inductor is doing. So if I were to plot things out here really quickly, I would have something like this. So this is IL of t measured in amps. And this is going to be time measured in seconds. And this point right here represents t is equal to 0. So for all points in time before t is equal to 0, or before our switch changes states, our current is going to have some constant DC value because we have essentially a DC circuit. So I'm going to call this region of time a DC steady state condition. And we already know that at DC steady state, our inductors look like short circuits. We talked about that last week. Okay. I'm going to call this time right here t is equal to infinity. Really, all I mean is a very long time after our switch is closed so that our transient has died out. And we know that for t is equal to infinity and beyond, our current is also 0. Or excuse me, not our current is also 0. Our current is 0 because our resistor has converted all of the stored energy into heat. Okay. So from this point on and to the right, we also have another instance of DC steady state. Everything that's going on between t is equal to 0 and t is equal to infinity is what's called our transient condition. And this represents how our circuit is behaving or responding to that change that happened whenever we flip that switch. Okay. So what we're going to spend the next several minutes doing is trying to figure out or come up with a mathematical model that will describe that transition from the DC steady state condition for t less than 0 to the DC steady state condition for t greater than infinity. Okay. So let's look at things really quickly. So during the transient condition, and I'm going to define that to be 0 plus is less than or equal to t is less than infinity. Our circuit is going to look like this. So I've got my current source here. So during the transient, my switch is closed at position B. Here's my resistance REQ and my voltage VR. Here's my inductance LEQ. My current IL and my voltage VL. So I can apply Kirchhoff's voltage law around that right-hand loop containing my resistor and my energy storage element, right? So if I apply KVL there, my stylus is acting up. Give me just a moment. So applying KVL around my right-hand loop, what I'll get is simply VR of t plus VL of t is equal to 0. Nothing particularly wild or crazy there, I hope. I can express both of those voltages in terms of my inductor current, IL. So for the voltage drop across the resistor, that's just Ohm's law, right? So that's going to look like R times IL of T. Excuse me, REQ times IL of T. And then for my inductor voltage, that's going to look like LEQ times the derivative of IL with respect to time. And this will be equal to 0. This is an example of a linear, homogeneous, first order differential equation. Now, I understand wholeheartedly that Math 245 is not a prerequisite for Circuits 1. So I don't expect you guys to know how to solve these types of differential equations yet. But we can really just kind of think our way through what our answers should be. So essentially, what I'm trying to find in solving this differential equation is the type of function that IL of t must be in order to satisfy this equation. So I'm looking for a function where the function plus its derivative might come out to equal 0. So the function and its derivative need to be effectively of the same form. So what kind of functions do we know that behave that way? I heard somebody, yes. An exponential function, absolutely. So let's say that we're going to take a guess. And this is an educated guess, but it's a guess nonetheless, that IL of t will be of the form AE to the ST. So I don't know how large my exponential function is initially. I don't yet know the rate at which my exponential function either decays or grows. So that's why I have a coefficient A that's as of yet undetermined and what's called an eigenvalue S that is as of yet undetermined. But we're going to substitute in this guess value and see what shakes out, okay? So if I plug this in, I'm going to have REQ times AE to the ST plus LEQ. So what's the derivative of AE to the ST with respect to time? SAE to the ST, okay? And all I'm going to do now is I'm just going to rearrange things a little bit, okay? So I can see that I have a common factor of A in both terms. So I'm just going to move that to the left-hand side. I've got a common factor of E to the ST in both terms, so I'm going to move that to the right-hand side. And here in the middle, I'm just going to put what's left. So unless I'm making a mistake here, this is going to look like REQ plus S times LEQ. And then I'll set this equal to 0. So let's talk our way through things here really quick. Okay? So one possible solution for this is that A is equal to 0. Okay? So if A is equal to 0, then I have 0 times a bunch of other stuff is equal to 0, which is very obviously true. So this is a solution, but it is a trivial solution. The solution where A is equal to 0 essentially means we have a condition where our inductor didn't have any energy stored in it to begin with. And so everything is 0 for all points in time, okay? That doesn't really correspond to what we have observed, right? Because we knew that our inductor had some amount of current flowing through it. Therefore, it had some energy stored. So A is equal to 0 isn't really the solution that we're looking for to describe what's going on in this particular case. Now, E to the ST can be equal to 0 under a couple of conditions. S needs to be negative, and we need to wait for some fixed amount of time. So if S is negative, eventually e to the st will trend towards 0. But that's not really good enough for us either, because we're looking for something that's going to satisfy this equation for all points in time, not just some specific points in time. So that leaves us with that middle bit right there, okay? So this is what's known as the characteristic equation for our circuit or our system. And essentially, we can solve for a value of S that is dependent on our circuit components that will make that characteristic equation equal to 0 for all points in time. So how would I solve for S for that REQ plus S LEQ is equal to 0? What would be my result? So negative REQ over LEQ. Absolutely. So let's look at the units of this thing just really quickly. Okay. So the units of resistance is the ohm or the volts per ampere. The unit of inductance is the Henry, which is a volt second per ampere, right? So I'm going to choose to write this as volts per ampere times seconds. So we can see very easily that volts per ampere is going to cancel volts per ampere, and we're just left with units of 1 over seconds. And 1 over seconds is more commonly referred to as the unit hertz, okay? Where hertz is what we use to describe frequencies. So this S is equal to negative REQ over LEQ is what's called the natural frequency for this system, okay? So it's the natural frequency because it's describing what's going on when we don't have any form of external excitation, right? We disconnected that current source at the very beginning. And so this is how our RL circuit naturally behaves in the presence of no external excitation, okay? So we can modify IL of t, our guess, to now say that it's going to be AE to the negative REQ over LEQ times time. So the only other thing we need to solve for is that coefficient A. Well, this is actually pretty easy to do because of the way that exponential functions work, right? So I could say that IL at 0 would be equal to AE to the negative REQ over LEQ times 0. But e to the 0 is literally just 1, which means IL at 0 is just A. I'm going to make a slight change here. Very, very slight. So I defined what's going on here during our transient condition to be from 0 plus beyond. So I'm going to replace that 0 with 0 plus here, simply because all of the circuit analysis and stuff that we've done to this point is only valid for t greater than 0 plus. And so if I substitute in that relationship, I finally get the result that IL of t will be equal to IL at 0 plus e to the negative REQ over LEQ times time. So this is how my inductor current is going to behave as a function of time during my transient condition. So if I scroll back up here to my graph, I can literally now just kind of plug in what's going on. So what we're expecting to see is that our inductor current is going to just exponentially decay during our transient. And that rate of exponential decay is dependent on the equivalent resistance and the equivalent inductance of the circuit, okay? Which should make sense, I hope. The values of the components should play a role in how the circuit behaves, okay? So we have solved this extremely generically on purpose. Essentially, any circuit that I can boil down to an equivalent resistance, a single equivalent resistance, and a single equivalent inductance is going to behave this way. Regardless of how complex it looks, if I can come up with a single equivalent resistance and a single equivalent inductance, I know 100% of the time it's going to work like this. So what I would like us to do now is work an actual example problem. And I'm going to show you guys kind of the algorithm or the approach that I use to solving these type of circuits, okay? So let's say that I have the following circuit. I've got a 64-volt source connected to a switch, and this switch is opening at t is equal to 0. And let's say that I'm interested in the following two things. My inductor current, IL, as a function of time, and this resistor current, which I'm going to call IR as a function of time, okay? So these are the two quantities that we are solving for, okay? So my first step in analyzing a circuit like this is always going to be to analyze our circuit at time t is equal to 0 minus. So this is the split second in time before our switch changes state. And it is representative of what has been happening from t is equal to negative infinity up until the moment right before our switch changes state. So because it's a DC circuit, it's going to have the same value for that whole chunk of time, right? So at this particular point in time, our switch was closed and we're at DC steady state. So our inductor is going to look like a short circuit. So I could redraw my circuit and it would look something akin to this, right? So here's my 64-volt source. Here's my 4-ohm resistor. Here's a 40-ohm resistor. Here's an 8-ohm resistor. This short circuit right here represents my inductor. because in a DC circuit, an inductor can be replaced by a short circuit. And here's my 48 ohm resistor. This is my current IL of 0 minus, and this is my current IR at 0 minus. So before we start analyzing this circuit, I think we can all hopefully make a pretty simple observation that 48 ohm resistor on the right-hand side is in parallel with an inductor, and the inductor is behaving as if it is a short circuit because we're analyzing a DC circuit. So the 48 ohm resistor is shorted out, which means it will contribute literally nothing. So I can ignore it for the rest of my analysis. Are we all okay with that? So recognizing that our 48 ohm resistor can be ignored, how might we analyze this circuit? I'm sorry, what was that? Why? So the 40 ohm resistor is not in parallel with the short. The 8 ohm resistor breaks that connection up. So we could do current division, but to do current division, we need to know a known current. So we could do a source transformation here to give us a known current to use. That seems perfectly reasonable to me. So if I did a source transformation effectively, let's see, I'd have 64 over 4, which I believe is 16. I'm going to have my 4 ohm resistor here in parallel. I'm going to have a 40 ohm resistor in parallel. And for what it's worth, the 8 ohm resistor is going to be in parallel as well, right? So hopefully we can all see this pretty easily. So the 8 ohm resistor, sorry, shouldn't have drawn it that far. The 8 ohm resistor, because of that short circuit, is very obviously, I hope, in parallel with the 40 ohm resistor. So I'm just going to draw it as if it was in parallel as well. And a couple of other things that we can observe. So obviously, this is IR at 0 minus, but that same current is going to flow through the short representing the inductor. So it's going to be IL at 0 minus as well. Are we all okay with that? So doing current division, I could say that IR at 0 minus is going to be 64 volts over 4 ohms. That's just my equivalent current source. Again, I believe it's just 16, but then I would have 1 over 8 ohms divided by 1 over 4 ohms plus 1 over 40 ohms plus 1 over 8 ohms. And this comes out to be 5 amps if I did my current division correctly, or I know I did the current division correctly if I put it in my calculator correctly. So before we move on from here, can anybody else verify that this comes out to be 5 amps? I've got some thumbs up. And for what it's worth, we also know that this is IL at 0 minus. So before we move on from here, does anybody have any questions, comments, or concerns about the analysis we did? Yes, sir. It will be. So our next step is going to be to analyze our circuit at 0 plus. And we are going to use the fact that the inductor current cannot change abruptly in redrawing our circuit. So you're a step ahead of everybody else, but that's okay. Any other questions, comments, or concerns? Okay, so let's go on to step 2. So this is a snapshot of the circuit the moment after the switch changes states, okay? So if we look back at our original circuit, since it was opening at t is equal to 0, we're now at the moment after our switch has changed states. So the 64-volt source is going to be disconnected from our circuit. So we're going to replace the switch with an open circuit. And I'll talk about what we're going to do with the inductor in a moment, but because we're in the transient condition, we are no longer looking at a DC circuit, so we at least certainly are not going to replace our inductor with a short, okay? So I'm going to draw things out here. So here's our 64-volt source. There's the open circuit replacing our switch. Here's the 4 ohm resistor. The 40 ohm resistor. The 8 ohm resistor. What our inductor is doing, we'll sort that out in a moment. And then the 48 ohm resistor over here. Okay. Exactly right. So we know that IL at 0 plus must be equal to IL at 0 minus, which was 5 amps. So essentially, we know that through that branch there that I haven't put a circuit element in, there is a fixed amount of current of 5 amps flowing down through that branch, regardless of whatever the voltage drop across that inductor was or currently is, okay? So some people choose to write this as an inductor, and then they just make a note that there is a fixed amount of current. I don't do that. I literally replace my inductor at t is equal to 0 plus with a current source, because the inductor at this very specific instant in time is behaving exactly like an ideal current source. The amount of current that's flowing through it is a constant fixed value, regardless of what it's connected to, what voltage drop appears over it, all of that kind of good stuff. So I'm going to replace my inductor with a 5 amp source, direction down, because we showed earlier that the inductor current at 0 minus was 5 amps, and the inductor current was defined with direction down, okay? And now what I'm trying to find is this current right here, IR at 0 plus. So before we analyze this guy, let's make another simple observation, okay? So the 4 ohm resistor is not part of a closed current carrying path, right? It's open circuited on the left-hand side. So that means that no current can be flowing through it, and therefore no voltage drop can appear across it. So this 4 ohm resistor contributes nothing. Are we all okay with that? Okay. So what does that current source see? Well, it sees 48 ohms of resistance on the right and 48 ohms of resistance on the left, because that 40 looks like it's in series with that 8, since we know no current can branch off and flow to the left of that open circuit. So how much current is flowing through that 8 ohm resistor? What was that, Matthew? 2.5, half, because it sees 2 identical paths. Right? So if we wanted to more formally do current division here, we certainly can. IR at 0 plus is going to look like 5 amps times 1 over 40 plus 8 over 1 over 40 plus 8 plus 1 over 48. But that is literally just going to come out to be 1/2. So I'm going to call this 2.5 amps. Any questions, comments, or concerns about the analysis we did here in step number 2? All right. Yes. So the voltage source is disconnected. If we look back at our original circuit, we're told that at T is equal to 0, that switch is opening up, disconnecting the voltage source. So the 64 volt source isn't connected to anything to be able to do anything. It's not going to show up, or it's not going to have any impact on our current division relationship because it's open circuited. So we know that that 5 amps of current is going to flow down. It's going to split between those 2 paths, but no current can flow this way because of the open circuit. Any other questions? All right. So the next thing we're going to do is we're going to analyze this circuit at T is equal to infinity. So a very long time after our switch changed states. Now, I am going to preface this by saying we're going to get 0 here. The reason why I am including this step is because of what we're going to be doing in Wednesday's class meeting. And so I just want you to be aware that this step is going to matter at a later point in time. But right now, every time we do it, when we're taking out our sources, it's just going to result in a 0 value, right? So essentially, step number 3 is analyze the circuit at T is equal to infinity. So at T is equal to infinity, our switch is still open. So here's our 64 volt source in series with an open circuit. Here's our 4 ohm resistor. Here's our 40 ohm resistor. Our 8 ohm resistor. So T is equal to infinity is DC steady state. So we're going to replace our inductor with a short circuit. Here's our 48 ohm resistor. Here is IL of infinity. And here is IR at infinity. So what are IL and IR going to be? 0, because literally there's nothing connected to the circuit to make them anything other than 0, right? So we could just say that IL at infinity is equal to IR at infinity is 0 ohms. And this will be true for any circuit where we're taking the sources out of the system. All right, so step number 4. Is going to be determine LEQ and REQ, that Q looks horrifying, during the transient condition. And I'm underlining this bit, during the transient condition. So essentially we're looking at our circuit for t greater than 0 plus to figure out what REQ and LEQ are going to be. So in this particular example, we only had one inductor. So I believe it should be pretty easy for us to figure out what LEQ is. It's the value of the only inductor in the circuit, right? So we could say that LEQ is, I believe, 2 henries if my memory serves me correctly. Yep. And I'm just going to put by inspection here. So the REQ that we're looking for is essentially the Thevenin resistance seen by the inductor during the transient condition, okay? So during the transient condition, our circuit looks something like this. Here's our 64-volt source. The switch is open. Here's a 4-ohm resistor, 40-ohm resistor, an 8-ohm resistor. Here's our inductor. Here's a 48-ohm resistor. We're finding the Thevenin equivalent with respect to the inductor. So I take the inductor out, leaving behind an open circuited set of terminals. And then because I'm finding the Thevenin equivalent resistance, I need to be looking at a dead network. So I turn the 64-volt source off. So what is the equivalent resistance that we see? Anybody care to venture a guess? 24, right? 48 in parallel with 48. So the 4-ohm resistor up top here is open circuited and doesn't contribute. So I see 48 ohms when I look to the left, 48 ohms when I look to the right. Those two are in parallel. So I have just 48 ohms in parallel with 48 ohms, which is 24 ohms. So there's my REQ and my LEQ. Before I move on from this, does anybody have any questions about what we did here? So I just want to reiterate, because this, I'll answer your question in just a second, Carter. So this is one of the places where I see students make the most mistakes, okay? So we need to be looking at what's happening during the transient condition. So essentially, looking at the circuit at t is equal to 0 plus is as good a place as any. Definitely do not do it at 0 minus, because that is before the transient condition occurred, okay? We're always finding the Thevenin equivalent, which means we need to be looking at a dead network representation. When we find the resistance, we're looking from the terminals left behind by taking the energy storage element out. If we had multiple energy storage elements, we would find the equivalent energy storage element by taking the equivalent resistance out and looking at. Carter, what was your question?
When we have like what in order to find the equivalence of inductance, what point do we add in circuit?
So we would take it with respect to REQ.
So wherever.
Yeah, we take the resistance out and try to find the equivalent inductance.
At two terminals.
Yeah, so if we take the resistance out, it's going to leave behind an open circuited set of terminals. Those are the terminals that we look into. Just like how we took this inductance out, leaving behind an open circuited set of terminals, and those are the terminals we looked into to find LEQ, or excuse me, REQ. So I wouldn't say make it open circuited at all of the resistance. So this is where it gets a little potentially tricky-ish, okay? So for a first order circuit where it should be fairly obvious if your inductances are connected in series, parallel, or something like that. And we'll work some example problems later on, particularly on Friday, that'll show us more what to do there. But essentially, if we can easily see how our inductances are connected, that'll make it easier. If we only have one resistance, then obviously we could just take that resistance out. It gets more complicated when we have several resistances and several inductances. So I'm not going to give you anything where it is difficult to find out what the LEQ should be, okay? The reason why is because if you can't combine the inductances into a single energy storage element, you don't have a first order system, and that's where our analysis stops in circuits 1. It's only in circuits 2 where we go into second order systems, and it's only in circuits 3 where we go into higher order systems than that. So the guide rails put in place by the class itself don't allow me to make that part complicated. So it's not a great answer, but it's an honest answer. Okay, any other questions about this guy? All right, so now we go to step 5, okay? So we are going to plug in the results of steps number 1 through number 4 into our generic equation. So I want you guys to not write things down for a moment and just kind of pay attention here for just a second, okay? So what we derived at the beginning of class was essentially this, okay? So we saw that IL as a function of time, and I'm going to do this as a piecewise function, okay? So we had, it would be IL at 0 minus for t less than or equal to 0 minus. That's just our DC steady state analysis occurring at t is equal to 0 minus. And then we had IL at 0 plus e to the negative REQ over LEQ times time for t greater than or equal to 0 plus. Everything that we derived was only in terms of the inductor current. But as it turns out, everything in our circuit is going to behave this way. So let me prove it to you very quickly. Okay, so let's stick with this for right now. Okay, so if I wanted to plug things in here, at 0 minus, our inductor current was 5 amps, right? And at 0 plus, our inductor current was 5 amps. And so we're going to have 5e to the negative. So we have 24 over 2 is 12 t amps for t greater than or equal to 0 plus. Literally just plugging stuff in, okay? Where, just to be clear, that 12 came from REQ over LEQ, okay? Well, we were also asked to find our resistor current, okay? Now, we observed way back here that essentially half of our inductor current is going to flow up through the 40 and then from left to right through the 8. So it would stand to reason, using current division, that IR of t is equal to half IL of t for t greater than or equal to 0 plus. So we would have something like, so what happened at 0 minus? What was our resistor current? It was also 5 amps. So we would have 5 amps for t less than or equal to 0 minus. And then we would have 2.5 e to the minus 12t amps for t greater than or equal to 0 plus. Well, what's interesting is that we would get that exact same result using this relationship if we replaced all of those lowercase l's with lowercase r's, right? So I want to explain why effectively everything is going to have this exponentially decaying style response. So if we look at this circuit right here, let's go back to the beginning, right? So when that switch opens, we know that whatever inductor current is flowing down through that 2 Henry inductor is going to split. Part of it's going to flow to the right and up through the 48 ohm resistor. Part of it's going to flow to the left and up through the 40 ohm resistor and then the 8 ohm resistor in series. Nothing's going to flow through the 4 ohm resistor because it's connected to an open circuit. No current's going to flow through that 64 volt source because it's connected to an open circuit, right? So we have a very good understanding of what's going on with all of our currents. So if the inductor current is exponentially decaying, all of the resistor currents that aren't 0 have to be exponentially decaying as well, because it's the inductor current that's driving everything. Well, using Ohm's law, if we know that our resistor currents are exponentially decaying, then the resistor voltages have to be exponentially decaying. And using KVL, we could then say that the voltage drop across the inductor must also be exponentially decaying. So essentially, if one of our elements, so our energy storage element, either an inductor or a capacitor, is behaving with that exponentially decaying response, everything else in the circuit will also have either an exponentially decaying response or a DC value. There will be no other options, okay? So we can put things in a very generic form that is applicable for literally everything, okay? So our generic equation is going to be this guy. So I'm going to say that y sub n of t, where that n stands for our natural response, is going to be y at 0 minus for t less than or equal to 0 minus, and y at 0 plus e to the negative req over leq times time for t greater than or equal to 0 plus, where y here is simply any current or voltage in our system. So as long as we are keeping track of it through all the steps, exactly what we did, we could just plug stuff into this generic equation, regardless of whether we're looking at currents, voltages, and we'll always get the right result. So this is the generic equation that I think that you guys should actually use for literally everything we're doing right now. So if we replaced all of those Y's with IRs, just for what it's worth, we would have IR as a function of time. So what was IR at 0 minus? Scroll up, you presumably wrote it down. or I say scroll up, go back a page. I'm the one writing the shit on a computer, but yeah. So Y is any voltage or current that we're interested in, so that we've kept track of. So in this case, I'm trying to find out what's going on with that resistor. So what was the value of the resistor current at 0 minus? 5 amps. What was the value of the resistor current at t is equal to 0 plus? 2.5 amps. E to the minus, REQ over LEQ is going to be the same for everything. So that's minus 12t amps for t greater than or equal to 0 plus. The exact same result we got using current division. It has to be. Okay. All right. So any questions about this example? Yes. I'm sorry, what? So the next thing that I want to talk about is what happens if we have an RC circuit. Okay. And I'm going to do this much more quickly because it is damn near identical to what we just did with RL circuits. Okay. So let's say that I have a generic RC circuit, something akin to this. So I've got some voltage source Vs. I've got a switch that's opening at t is equal to 0. And over here, I have some resistance REQ connected to some capacitance CEQ like so. I'm going to define the voltage drop across my capacitor, VC of t like so, positive polarity on top. And then I'm going to say that this current flowing down here is my capacitor current. And this current flowing down here is my resistor current. So hopefully we can all see that for points in time less than 0, when our switch has been closed for a very long time, our capacitor is just in parallel with our voltage source. And so VC at 0 minus would just be Vs. And because we know that our capacitor voltage cannot change abruptly, whatever value it had at 0 minus, it has to continue having at 0 plus. So that is also just going to be Vs. So essentially, our capacitor has some amount of energy stored. And then as we switch that voltage source out, the capacitor is gradually going to transfer its energy over to that resistor. So a very similar situation to what we had with our RL circuit, okay? At t is equal to infinity, we should see that our capacitor voltage is 0 because all of the energy that was initially stored in our capacitor was then converted into heat by that equivalent resistance. So during our transient condition, we could say that the current IR of t plus IC of t must be equal to 0 amps, right? So that's just applying KCL at that topmost node. So the current flowing down through the resistor plus the current flowing down through the capacitor plus 0 current flowing to the left through that voltage source because it's switched open is equal to 0. I could express both of these currents in terms of my capacitor voltage. So that would be VC of t divided by R plus C dVC by dt is equal to 0. And I have another first order differential equation. So I'm going to use the exact same guess value that worked for me last time. And if I substitute this in, I wind up getting 1 over r times ae to the st plus c times sae to the st is equal to 0. Rearranging it slightly, I have a times 1 over r plus sc e to the st is equal to 0. This is my characteristic equation, where S, it turns out, is going to be equal to negative REQ times CEQ. Sorry, I forgot all the EQs. There we go. And let's see. So if I plug that in, I get VC of t is equal to AE to the negative REQ CEQ. Actually, hold on. My mistake. That should be 1 over REQ CEQ. That's what I get for doing it quickly. Times time. And then VC at 0 is going to be AE to the 0. And we know that E to the 0 is simply 1, which lets us say generically that VC of t is going to be equal to VC at 0 plus E to the negative t divided by REQ CEQ. And this is valid for 0, t greater than or equal to 0 plus. So derivation, very, very similar. Result, almost exactly the same thing, except that now our exponential decay is governed by the value of the capacitance and the resistance, right? So essentially, this is going to be our new generic equation kind of thing. So let's look at an example to see how we can put this into practice, much like we did for our inductor problem. All right, so let's say that I have something like this. So here's VC of t that I'm looking for. And while I'm at it, let's go ahead and find this resistor current as well. So until we get to step 4, our process is going to be exactly the same. We're going to analyze our circuit at t is equal to 0 minus, then analyze it at t is equal to 0 plus, analyze it at infinity. The only thing that's going to change in step 4 is just find CEQ instead of LEQ, and so on and so forth. So process is damn near identical, okay? So let's look at step 1. Analyze the circuit at t is equal to 0 minus. So at t is equal to 0 minus, our switch is closed. So our circuit's going to look something akin to this. So here's a 10-volt source. $200 ohm resistor, another 10-volt source. We are going to have just a short circuit over the top like so. Here's our 250 ohm resistor, our 50 ohm resistor, and then because we're at DC steady state at t is equal to 0 minus, we're going to replace our capacitor with an open circuit. And then here is the IR at 0 minus that we're interested in. So does anybody have any thoughts on how we might analyze this guy? Are there any things that we can do to simplify things? So the 50 ohm resistor isn't doing anything because it's not part of a closed current carrying path. So essentially that means that our capacitor voltage is going to be the same thing as the voltage drop across the 250 ohm resistor. So if we find that current IR, we can use Ohm's law to find VC, or if we find that voltage VC, we can use Ohm's law to find that current IR. So anybody have any thoughts on finding either one of those two things? So I've done it in my head, but I also realize that I am a jackass with a PhD who's done this kind of stuff hundreds of times, and you guys are not. So I'm going to do something that will hopefully make it very obvious to you what the answer should be here. I'm going to identify nodes. So now that I've identified my nodes, how are the 10-volt source and the 250 ohm resistor connected to each other? Nope. They're in parallel because they both share the orange node on top and the green node on bottom. So what's VC at 0 minus? 10 volts. Anybody have any questions, comments, or concerns about that? Yes. So the 10-volt source in the top middle is between the blue node and the orange node. So it matters in as much as it could be potentially driving. So there's going to be some current flowing through the 200 ohm resistor because of the voltage difference between the blue node with respect to the green node and the orange node with respect to the green node. But that's all the 10-volt source in the top middle is going to be doing, is just pushing some current through that 200. Real. Good. So wait, KVL defined IR? So we could do KVL to find VC. I mean, we could do KVL to find IR, but it's overkill at this point because we know the voltage drop across that 250 ohm resistor. So we could just use Ohm's law, which will be our next step. But I just want to make sure that everybody's catching what I'm throwing here, that The voltage drop across the capacitor is the same as the voltage drop across the 250 ohm resistor because you correctly observed that that 50 ohm resistor isn't doing anything. And the 10-volt source is just in parallel with the 250 ohm resistor because of that short along the top there. So IR at 0 minus is just going to be 10 volts over 250 ohms. Comes out to be 40 milliamps from Ohm's law. All right. So now let's look at step 2. Where we analyze the circuit at t is equal to 0 plus. So our circuit's going to look something like this. Here's our 10-volt source. Here's that 200 ohm resistor. The second 10-volt source. Here's that path over the top. But since the switch is now open, I'm just going to replace that short with an open circuit. $250 ohm resistor through which we have a current of IR at 0 plus flowing. 50 ohm resistor here. And now we need to talk about what to do with our capacitor. So we know that our capacitor voltage at t is equal to 0 plus must be equal to the capacitor voltage at t is equal to 0 minus, which was 10 volts. So we have a fixed amount of voltage, regardless of what's connected to it, how much current is flowing through it, etc. So I'm going to choose to replace my capacitors at t is equal to 0 plus with a voltage source. So we replaced our inductors at 0 plus with a current source. I'm going to replace my capacitors at 0 plus with a voltage source, where my voltage is going to have the same value, 10 volts, and same polarity as VC at 0 minus. Okay. So all we need to do now is analyze this circuit to find out what IR at 0 plus is going to be. Brielle, how may I help you? So our switch was opening at t is equal to 0. So it was a short circuit at 0 minus, and it will be an open circuit at 0 plus, based on the way that that arrow is drawn. For what it's worth, in the problem statement on, I believe your homeworks and definitely on the exams, I also usually write it out so that there's no ambiguity. And I'll say the switch is closed at, for a long time before opening at t is equal to 0 or something like that, so that it's very obvious what you're supposed to be doing. All right. So I want to make a couple of simplifications to this thing. Okay. So the first simplifications that I might make is it going to mess anything up if I literally just erase those open circuited paths right there? No, they're not doing anything. So the reason why I erased those is because I wanted to make it really, really obvious that those two 10-volt sources are in series with each other during the transient condition. So they're in series with each other and they have opposite polarities. So 10 volts minus 10 volts is just 0. So realistically, I can get rid of both of those guys, leaving behind just that circuit. And that is something that we can analyze pretty darn easily. So anybody have any thoughts on how we might find IR at 0 plus? So We could do voltage division to find the voltage drop across the 200 in parallel with the 250, and then use Ohm's law to find IR at 0 plus. Or we could do a source transformation and use current division to find IR at 0 plus. So we could also do that. So we could find REQ to find the current flowing through the 50 ohm resistor and then use current division to find out how much splits off. Yeah, so we've thus far now covered 3 different options, all of which are exactly 2 steps. So let's do, I'm going to do the voltage division route just because we haven't done voltage division today. So essentially what I'm going to do is I'm going to define this voltage, so positive polarity here, negative polarity here, as Vx. And I could say that Vx is going to be equal to 10 volts times 250 times 200 over 250 plus 200 over 50 ohms plus my numerator again, 250 times 200 over 250 plus 200. So if I throw that into my calculator, if I type this in correctly, I got 200 over 29. And from here, IR at 0 plus is just going to be Vx divided by 250 ohms, which I get to be 27.586 and some change milliamps. So before we move on from this step, did anybody else get those values? Okay. Of course, if we were so inclined, we could have also done, mesh nodal and all of that kind of stuff as well, but I feel like that would have been overkill, which is why I didn't bring it up. All right, so any questions about the analysis that we did here? Because we did several simplification steps. I just want to make sure that you guys were catching what I was throwing there. Getting rid of those open circuited terminals to make it more obvious that the 10-volt sources were in series because they were of opposite polarity. They cancel each other out, leaving behind short circuits in their place. And then we have a pretty darn simple, I think anyway, circuit to analyze. Any questions? All right, so step number 3 is going to be to analyze at t is equal to infinity. I'm going to skip step number 3 because the answer is literally just going to be 0 because quite obviously during the transient, those voltage sources cancel each other out, which means we don't have anything connected to do anything. And we're just going to jump straight ahead to step number 4. So in step number 4, we are going to determine CEQ and REQ during the transient condition. So I hope very obviously that CEQ is just 5 microfarads because it's the only capacitor in the circuit. So how could it be anything else? Now we would need to find REQ. So I'm just going to draw the circuit out here. So 10-volt source, 200 ohm resistor, 10-volt source, 250 ohm resistor, 50 ohm resistor, capacitor, right? I'm finding the Thevenin equivalent resistance with respect to the capacitor. So I take the capacitor out and I look in through its terminals. And I need to be looking at a dead network, which means those 10-volt sources turn off. I mean, since they canceled each other out, they effectively turned off anyway, but just to be more formal. So I think I see 200 in parallel with 250 in series with 50. Which comes out to be 1,450 over 9 ohms, or 161.111 ohms if that floats your boat. And now for step 5, we simply put stuff into our generic equation. So for us, with this RC circuit, our generic equation will now be y sub n of t is equal to y at 0 minus for t less than or equal to 0 minus, and y at 0 plus e to the negative t divided by REQ for t greater than or equal to 0 plus. So for our capacitor voltage, this is going to look like 10 volts for t less than or equal to 0 minus, and then 10 e to the negative. So let me multiply this guy by 5. And then I do 1 over that. One 1.241 times 10 to the minus 3 t volts for t greater than or equal to 0 plus. Just to make this incredibly obvious, this is 1 over REQ times CEQ. Oh, sorry. No, you're right. Sorry, I just put REQ. It should be REQ times CEQ. Thank you for that, Carter. Trying to give you guys some time to actually work on the ICA, but it's not looking like that's going to happen too much. Sorry for the mistake because of hurrying. So for the current IR of t, similar situation, right? So the value for IR at 0 minus was 40 milliamps. T less than or equal to 0 minus. And then we had, I think it's like 27.586. So T greater than or equal to 0 plus. So it's literally just plugging stuff in. Okay, we covered a heck of a lot of things today. There technically is still 13 minutes left to work on the ICA. So realistically, you could probably knock out any individual problem, but probably don't have enough time to do more than one problem. So just pick 1, 2, or 3 and work on it. And if you have any questions, I'll be happy to answer. Yes, ma'am. So, yeah. So step number 3 is to just analyze the circuit at t is equal to infinity. Replace that inductor with a closed circuit. Exact same circuit, so replace the 5 amp source. That's what we were solving for previously. IR and IL. Jonathan, what's that?
Sandy check, was the capacitor in this problem 5 microfarads or 5 If I ended up with a natural frequency
Oh,
10 to the 3.
So I put just 5 as if it were 5 farads, so that's just me forgetting the units there entirely. So no,
Okay, so
you're,
it shouldn't be 10 to the -3, it should be 10 to the 3.
yeah, let me correct that, but thank you for pointing that out. Yeah, so when I was doing this guy right here, calculating 1/REQ times CEQ, I literally just put in 5 for my capacitance instead of 5 times 10 to the -6. So ultimately, that's just going to change that -3 to +3. So sorry about that.